Welcome to Embedded System and Design. Today we are going to start the topic, the typical embedded systems, which we have discussed earlier. So the embedded system majorly contains these blocks. One is the memory, right? This unit, memory and system core, right? It has I/O ports, sensors, output ports, that's actuator, and other supporting integrated circuits and subsystems, right? So in which memory are different type. So memories are primary memory, secondary memory. So basically we here discuss two types of memory. One is the data purpose, the another is the storing the instructions. So which memory you can use for the data purpose? May I know that? Can anyone answer? For storing the data, which memory you can use? For storing the data, how many types of memories? One is the RAM, right? One is the RAM, and I think it has the reverse is showing. One is the RAM and the other is the ROM, read-only memory, right? So in which you can store the data, right? In RAM, what you can store?
Data.
Data. In the ROM,
Programs
you can store. So which is the permanent memory?
RAMs.
ROM is the permanent memory, right? So RAM is a data purpose and a ROM is for the program or instruction you can store. So here we can call ROM is non-volatile memory and RAM is volatile memory, because once the power goes, the RAM memory will be the content which is retained, the data which is retained in the RAM will be erased, right? But in the case of ROM, it is not like that. It can store permanently. And you can see the communication interface which is connected to the system core, the right side, this one. So this system core has, you can see the image, some cables, USB cables like pen drives, right? So this communication interface, you aware of that the communication interfacing devices are three different types. You can call them onboard communication devices, right? And product based communication devices, or otherwise you can categorize them as wireless device and wired devices. So wireless devices, you are aware of that, Bluetooth, right? Wi-Fi, and these are the wireless. And wired communication device are USB cable, right? Universal serial bus, RS232, IEEE 1392. These are the cable, depends on the application requirement of the user. You may interface with the system core. So you are looking these devices side by side, but all are inside this system core itself, right? The memory which you are looking in this block will be part of the system core, and I/O port sensors and this I/O port activators all are inbuilt in a system core, and that system core is developed by using any one of these technologies. One is FPGA. What is FPGA stands? We have discussed it. FPGA stands for field programmable gate array, right? ASIC is application specific integrated circuit. DSP, digital signal processing. SOC is system on chip. So microprocessor or microcontroller. So both the versions are available in this, right? And this is the embedded firmware. So in the memory, the embedded firmware or the software will be placed in this memory in the form of instruction, which you can monitor, control or guide the system core. And you could see left side input output ports, sensor. There are many types of the sensor. Basically, sensors will be acting as an input device or output device. Sensor will be acting as a input devices, and output devices you can observe here LED and some buzzers, right? And other supporting integrated circuits and subsystem based on the application it will be used. So this is the basic, the minimum criteria for the particular embedded system, right? For the embedded system, any embedded system, if you look for the any company, right, there are so many companies which are like Motorola, Texas, Intel, right? These are the world companies which build manufacturing the embedded system, FPGA, mental graphics. So this embedded system, so any embedded system which has this following configuration: memory is must, system core is must, right? Whether one company may use system core FPGA, other company may use ASIC. So based on their convenient, the product availability, the demand, the user which one like measure, they can manufacture will go according to that. So coming to this, the core of the embedded system, the core of the embedded system falls into any one of the following categories. One is the general purpose and domain specific processors, right? What is general purpose processors and domain specific processors? General purpose processor is like a mobile phone. You can use for sending the information, receiving the information, watching the movies, taking the pictures. So processor is doing in that general. All the tasks will be done, right? Generally in mobile, the Qualcomm processor can be used. That is, what is the name of the processor? Snapdragon. The version will be there. So the latest version based on the year, every 1 year, 2 years, the technology is transforming. And domain specific processors. Domain specific processor means the particular application depends on the application. Generally, embedded system is used in automobile. For example, vehicle, a car, BMW car. It has certain parameters of application in which we can incorporate a domain specific processor. Right? In home appliances, right? In micro oven, in refrigerators, that specific related processor we can monitor, fix that, right? So it can be used, maybe processor, it can be microcontroller, it can be digital signal processor. How you are going to that based on the applications, right? And coming to the PLDs, programmable logic devices, right? It has some gates. It can have like full adder, half adder, some arithmetic operation can be performed using PLDs, and you can having ASIC, application specific integrated circuit. It depends on these commercial or the shelf components. So any one of the among the four you might or you may use as a system core, right? And coming to this general purpose processor versus application specific instruction set processor. So as we noticed earlier, general purpose processor designed for general computational tasks, arithmetic, logical, right? Some scientific related mathematical computation like MATLAB, generating sinusoidal signal, or continuously monitoring the temperature. That purpose you might use the general purpose processor. And ASIC, ASIPs are can be used for the domain specific applications. GPP means general purpose processor. For the R application, you might use that, right? And coming to the next slide, you have, wait a minute. Somebody send a message. It's not changing. Let me check. Is it visible for you? Slide is visible.
Yes, sir.
Why it is not changing? Right now, okay. Right. So microprocessor. So which is developed, the first microprocessor is 4004. The 4 indicates in which is a 4-bit microprocessor. This 4 indicates the first microprocessor in the world introduced in the year of 1971, introduced by the Intel company in the year of 1971. Currently, it is also used in normal calculator, generally used in the kirana shops, in stores. It may be used for some computation, basic calculation, for adding some numbers, right? And after that, it is developed after 1971. In 1972, 8085, 8086, followed by the next years. So as the years are going, the size and the number of bits its storage or process is increased. 4004 means it has only 4 data buses. In 8085, it is a 8-bit microprocessor. It has 8-bit and 8 buses or 8 address lines. Coming to 8086, it has, for example, 4004. It is a 4-bit. 8085, it is an 8-bit processor. 8086, it is a 16-bit processor. Where it can differ? It differs in the data bus size. So number of data buses are 16 here, here 8, here 4. So that it can process in one cycle 4 bits. It can process in one cycle 8 bits. It can process in one cycle 16 bits. Cycle is nothing but this, right? From here to here, one cycle, right? Coming microcontroller. So it is a highly integrated silicon chip. So both these basically processors, either it is controller or processor, manufactured by using VLSI technology. So silicon, you are aware of that material in the periodic table. So silicon chip containing CPU, central processing unit, scratch pad. So what is the difference between processor and controller means? The processor has only CPU. Inside the chip, the processor has only CPU, central processing unit. It means it has registers, some control buses, address bus, data bus. But microcontroller has, apart from this CPU, it has RAM memory. You are aware of that 8051. It has certain amount of memory, on-chip memory. RAM memory, how much? Do you remember anyone? 128 bytes. RAM memory and ROM memory 4 kilobytes. It has 4 kilobytes. So the major difference between the processor and controller is processor doesn't have on-chip memory, but controller has on-chip memory apart with the some additional equipment also there. Right, additional means sometimes LEDs, LCDs, display devices, keyboard. These are the placed on that. Depends on the company. Every year, every 2 years, the technology is upgrading the number of components on a same area. Every 18 months, the number of transistors on each doubles. The technology name is called. Do you remember that? Which law it is? Moore's law. So he stated that every 18 months, on a same chip area, the number of devices may double, right? The difference between the processor and controller, right? So processor has only CPU, which we discussed. It has CPU, controller having CPU, RAM, and special and general purpose registers, arrays. These devices, RAM or flash type, it depends on memories, which we have discussed. Different types of memories are there, right? NVRAM, dynamic RAM, right? UART, universal asynchronous receiver transmitter. So the major point to conclude in this first point is processor is used for the general purpose for variable task, but the microcontroller is used for the only specific applications. This is used for only specific application. And coming to this second point, the processor is a dependent unit. Why processor is a dependent unit? Because the processor doesn't take its input its own. It doesn't have to display the result. So you have to give some inputs to the processor. For example, you are going to give 2 bits information adding 7 plus 6 to add the processor. You must have a input device to give the keyboard is required. To display the result, it should require monitor. So you should connect your microprocessor output device as monitor, input device as a keyboard, so that that 7 plus 6 will be displayed, added and displayed. The addition will be performed by the processor, but without keyboard you can't give the input to this, and without monitor you can't display the result. So it is a dependent unit. Processor is a dependent unit, but this is a self-contained device unit. Self-contained unit because a microcontroller has on-chip memory, on-chip inbuilt devices. So automatically it will take, once you give the values, it has keyboard, it has a display device, LCD display is already inbuilt on the chip. So it is a self-contained unit. Means I'm not saying that it can do major functions, but a microcontroller, if you build with major components, it can do major tasks. But like the course which we have in the programming lab, certain languages, C language or embedded C, that program you can easily run on the microcontroller without adding keyboard and display devices, because a keyboard is there inbuilt on chip itself. The LCD display is there, you can see the outputs. And most of the time, the third point, general purpose in design and operation. General purpose in design and operation, and the mostly application oriented are domain specific. I might be design a microcontroller for particular temperature monitoring in a room. I might be design a microcontroller for I can use for sensing the temperature in a room or water level monitoring. Right? In micro oven, whether food is cooked or not. In even electric rice cooker, once the rice is over completed, I can use there to display the symbol, some light. It is completed like yellow color. If it is not still cooking, red color. So like this, these are the applications for the major differences between the processor and the microcontroller. Coming to the digital signal processor. So digital signal processor is nothing but not new. The hardware architectural part in the DSPs, digital signal processor, is different. But inside the processors and controllers remains the same, but the program based on the algorithms, the internal hardware will be changed, right? For example, you are using full adder. So full adder having how many inputs? 3 inputs, right? Full adder has 3 inputs, A, B, C input. How many outputs? Full adder output, sum, right? Sum you will get and product you will get. So full adder design can be designed by using what? You can use by which gates? Anyone? Full adder circuit. You can use universal gates. What are the universal gates? What are the universal gates? NAND and
Nor.
NAND and NOR. Good. NAND and NOR gate you can use, and you can design the full adder circuit which can add. You can also truth table, right? The truth table contains inputs like A, B, and C. Here you can use sum and product. So here the input A, input B, input C in. So what you can give 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, like up to 1, 1, 1, last 8th bit. So sum 0 plus 0, 0 plus 0, you can add this. So you will get this. So adding this, you get a summer circle. So based on the truth table, sum and the product, you have to draw the K map. It is a 8-bit, no? 8-bit. So you have to draw the, use the K map, right? You can use the K map, A and BC in. You can map that and you can simplify the Boolean algebra. So what you get here? A bar, B bar, C in, again BC bar, BC, B, C bar. So whatever the ones and zeros you will get now here, that can be, sorry, sum and product. So for sum, you get one K map. For product, you get another K map, and you will get the Boolean function. Right? F of ABC in equal to sum. For sum, you will get one equation. For product, you will get another equation. Based on that equation, you have to use the gates. So those gates are there inside. Now, this is a small DSP block. Let us consider digital signal processing. So what I mean to say is, in DSP board, there is no software. In DSP boards, there is a architectural hardware is there. That hardware can do the computational task. But in the case of earlier discussion, the processor and controller, it have hardware, but the running in between that is the software. The data will be with the instructions of program. Here, the commands will be given and the hardware architecture is there. So, generally by using the DSP processor, you can perform the computational analysis such as Laplace transform, Fourier series, Fourier transform. So, Fourier series is Fourier transforms are generally used for transforming signal, periodic signal to non-periodic signal to periodic signal, linear system to non-linear systems, time invariant system to time variant system. So depends on that hardware architectural behavior, these boards are used. So generally it has some structural algorithms, butterfly algorithms, right? Circular calculations, linear calculations. So for that hardware is there, like a K map, you have to simplify and that design will be there. So like DSP board has many applications, arithmetic, logical applications, but when compared to the processors, the application size will be increases. 64-bit processor. In that, DSP boards will be used, right? And this is the RISC and CISC, a very important comparison. Reduced instruction set computer and complex instruction set computer. So earlier we have noticed this. So the preferable architecture for the processor. See, generally RISC and CISC, it is not the architecture. I can say the RISC and CISC is not the architecture of the processor. The architecture of the processor, it depends on the Harvard architecture and Princeton architecture. And this comes into the picture when the way of software, which type of software you are loading in an embedded system, right? In earlier block, we have seen embedded firmware. Could see here, the first slide, here, embedded firmware or embedded software. So the software means what? Instructions. The instructions which we are storing in the memory, that is ROM memory, where you can store instruction in the read-only memory. So in this read-only memory, right? In this read-only memory, the CISC type of architecture or RISC type of architecture, instruction you can store. The major difference between the RISC type and CISC type is the instruction in RISC are uniform size. All the instructions are uniform size. But in the CISC type of architecture, the instructions are variable length size. For example, recently, just now we have seen full adder. So for the full adder, the CISC type may be having 7-line codes, 7 lines code, and the RISC is having 3-line code or same 7-line code, same 7 lines code, but the code in RISC size, first line, second line, third line are uniform size. For example, 1-line code having bits 7 bits, second line code having 7 bits, third line code having 7 bits, because all line of code having uniform size. But in CISC type of instruction type, all the 7-line codes are not 7 bits, maybe 5 bit one code, right? Another is 7, another is 9, another is 11. So each line has variable length. So because of that, storing in the memory is difficulty. In which location you can store. Also, retrieving the data back also, it will take time. Right? For example, if you are putting regularly one item in your kitchen, for example, oil you put, right? Kitchen related, all the goods you can put at one place, and some if you put other place. So to go from kitchen to that place will take time. No, if all the items are placed at one place, it will quickly can retrieve that. Same way, CISC type of means variable size. It takes time to retrieve back. That is one major thing. You please notice. I request you to remember RISC and CISC type. The major difference is RISC type of instruction length size are uniform. Either it is 1000 instruction or 1 lakh code. All the 1 lakh code are uniform size. But in CISC, same it is having 1 lakh code, but it doesn't have or it doesn't follows the uniformity between size of the code. Right? That is the one major point you notice here. The RISC and CISC. Right? And the number of instruction easier for the user is RISC type and CISC is complex. So another important point I could remember you in the context of hardware, the person who developed CISC is thought that should not burden on compiler, right? Should not burden on the compiler such a way the instruction must be executed. But the scientists who were developed this RISC type architecture, they thought that no problem, it should be easier for the user, even it is burdened to the compiler. So they didn't bother about the compiler, what might be the risk it is taking, but they developed it is means the RISC type of architecture is easier for the man or the user just to give the command. The rest of the things will be, for example, execute a line of 1 lakh code. It can run the compiler 1 lakh times. But these scientists thought that you should complete prior the compiler, so give the compiler less time to execute. So when the compiler taking less time means who will take more time? As a user has to take more cautious. Because of that reason only the code is increasing in this. So every line you have to write. For example, the latest you know that Python, C and Java. So for example, a multiplication of 4 by 4 matrix in C language, you may take 20 or 25 lines. But in Python, it will take 3 to 4 lines. Right? So what you are taking in the C language, the compiler doesn't execute that many. That 4 by 4 matrix is a similar 2 line or 3 line. So you 20 line you are writing means what? You are reducing the complexity of the compiler. But in the Python, just you giving the 1, 2, 3 lines code, the rest of the things it will taking one. Means compiler taking more time in the Python. But in the case of C language, you are taking time to write each line, giving each command of input in the matrix. You have to read that, scan it, and you have to give it. So that is the difference between the RISC and CISC type. So RISC type, the second point I am going to notice you that a RISC type architecture, compiler takes more time to execute and less code more time. But in CISC type architecture, compiler takes less time to execute and the user has to take more time to give the instruction. Because of that reason, CISC type of programming having more line of code. Maybe it is around the RISC type of architecture having uniformly 278 instruction in 8086. Same CISC type is having around 1024 instruction. Right? So the number of codes or instruction in the RISC type compared to the CISC is less. Right? So this is the basic difference between the RISC and CISC. And mostly nowadays, all the companies are using a RISC type architecture. Right? Another 5 minutes, I will complete the today's class, and we'll discuss Harvard versus Van Neumann processor as the controller architecture. So already you know this. So input, CPU and memory. So single shared bus. And here you could see the Harvard architecture. In the Harvard architecture, CPU is there. In the Van Neumann or Princeton architecture also CPU is there. But the bus you see here, this single bus is shared by the IO devices and CPU and memory. You can notice here the important point you need to understand between these two architecture is, here memory is means what? Memory are two types. One is the RAM, other is the ROM. And you are well aware of that. RAM can store the data and ROM can store the program or instruction. Right? So this is about the Van Neumann architecture. Now come to the Harvard architecture. CPU is connected this side, program memory. Program memory means what? Tell me. RAM or ROM? Please respond. Dear student, are you sleeping? Please wake up. Program memory means what? Respond. Data memory?
RAM.
Right. Thank you for responding. I'm waiting for the answer. So RAM means data memory, program memory means ROM. Right? The same I have represented in this. So you notice here in Van Neumann architecture, single memory chip is there. Inside the memory chip, you have both RAM and ROM. You notice here that in this memory, programs and data are together, clubbed. But you notice in a Harvard architecture, data memory separate, program memory separate, and it has two buses, the left and right. So whenever it requires simultaneously in one cycle, it can retrieve the data of programs and data of information. Right? So this is the faster. So how you can differentiate between the Van Neumann architecture and Harvard architecture? In Harvard architecture, program memory and data memory are separately connected to the CPU. And you can notice here in Van Neumann architecture or Princeton architecture, program memory and data memory are clubbed in a single chip. But here is two separate chips. So that is the difference. You please notice here. Right? Is it clear? You can see here Harvard architecture and Van Neumann architecture. Separate buses for instructions and data fetching in Harvard architecture. Already we noticed. And Van Neumann single bus. So single bus means it will take time now. If it is transferring data, till the data is complete, you can't transfer instruction. Right? Here. In this, If it is sending, the directions are both sides, so it is known as bidirectional. If direction is only one side, it is unidirectional. So all the buses see here bidirectional. This is also important. Bidirectional means this bus may give input to this memory, or this memory can read out. So memory write, memory read operation are there. Based on that criterion, it has bidirectional. So if it is transferring data to the CPU, till the data is complete, it has to wait for the instruction to transfer. But here that is not the case. If this is transferring instruction, this bus can transfer the data. So Harvard architecture is faster. Might be 2 chips, cost might be simply normally more than this Van Neumann, but the speed point of view, Harvard architecture is faster. Right? Coming to the second point, EGL2 pipeline. So high performance can be achieved. Pipeline means you know that fetch, decode, execute, memory write, right? Memory read, memory write, and memory write. Right? So pipeline is possible in Harvard architecture. Why it is possible? Because 2 separate memories it can handle. So low performance when compared to the Harvard architecture, because pipeline can't be possible. Already noticed now, simultaneously it can't transfer the data and it can't transfer the programs. And comparatively high cost, because 2 chips you are using, one single memory chip, you are inbuilt in that RAM and ROM, so that the cost is less. No memory alignment problem, because separately storing, you are storing separate memory, no? Here and here separate memory, no problem with the alignment. No aligning data from one location to other location. Alignment means one location clubbing with the another. So that is not an issue in the Harvard architecture. Allows self-modifying codes. It means it has issues with the alignment. One memory of data. For example, 4 byte is there, each member location. If the instruction is coming 3 byte instruction, so 3 will be stored and the empty location will be stored with some other line code, right? Like that. So alignment is that means already I have noticed this many times. So since data memory and program memory are stored physically in different location, no chances for accidental corruption of program memory. So here accidental corruption of the program memory is there. Chances is there. So we'll stop today here for the today's class. Thank you for joining with me. Right? And many students are absent. So please join from tomorrow onwards based on the timetable which is shared with you. I will take the class during that time. Thank you. Thank you for joining with me.